Hello everyone. Today I'm going to continue with the sessions related to the bar problems or the contents related to the bars. Uh, Previously we have done the solutions for a simple bar problem and also the derivation of stiffness matrix as well as the stresses generated in the bar element in terms of matrix form. So today we will apply the same principles that we have used in the previous problem into the next problem, which is our stepped bars. Okay, so let us look into the questions directly. Find the nodal displacement stresses in each element for the figure shown below. Take area of cross section A1 is equal to 200 mm square, area of cross section A2 is equal to 200 mm square, and Young's modulus of both the materials will be 200 gigapascal. Okay, and let us look into the actual component where the first element or the first bar which is situated here, which is of length 200 mm, and second one which is of 100 mm, where one end is fixed, that is the element 1 left end portion is fixed, and on the right end we are having one load. So if you closely observe, we are having two loads. One is 1000 Newton, which is applied against to that bar 2, and 500 Newton to the right side. So we are having two loads and one support conditions. Okay. So let us look into the steps related to this problem. So the first one, while explaining this, I will relate this with the steps involved in FEM that we covered in the previous model 1. What is the discretization of the structure? So I am going to discretize the whole structure, and while considering this, you need to go for its axis. So the first thing is consideration of the coordinate system. The coordinate system I will consider in this direction, that is along the direction of right side. So that's what which is provided. So first consider the direction of the axis. Okay, after that discretization of the structure. So the simple discretization for this one that can be done by taking the bar 1 as a single element, bar 2 as a one more element. So two elements are created, first element and second element, so which is connected by three nodes. So node 1, node 2, node 3, where node 2 is shared by both element 1 and element 2. Okay. So after this, the next step is where we should, previously I should find out what is the related contents with respect to the element 1 as well as element 2. So that is useful for stiffness matrix, where if you recall the whole equation, it is nothing but AE by L multiplied by 1 minus 1 minus 1 1 matrix. Okay, so where area of the element 1, that is 200 mm square, it is given in the problem. Length is also given 200 mm. Young's modulus is also given 200 gigapascal. So coming to the element 2 is also having the cross sectional area 200 mm square, and what we call the length will be 100 mm, and Young's modulus is also 200 gigapascal. So let's look into the next step, that is derivation of element stiffness matrices and load vectors, that is for element 1 and element 2. Okay, so element stiffness matrix means I should calculate stiffness matrix for all the elements situated in the problem. So here we are having two elements, so I should calculate two element stiffness matrix. Okay, so if you look into the equation and if I substitute all the things, so there is a small mistake in the problem statement. So A2 should be 100. Okay. So where we are in the place of calculation of stiffness matrix. So if I go for the element 1, where the suffix 1 I am going to represent for the stiffness matrix A1 E1 divided by L1. So you know A1 is equal to 200 mm square. I am going to substitute that. Young's modulus is 200 GPa, which is nothing but 2 into 10 raised to 5 divided by length 200 mm. So if you observe once again, so all the things that I am substituting, it is in terms of mm square. Okay, mm square, Newton per mm square, and length is in mm. So take care of the units, and after that you do the simplification. So if you do the simplification, I got the solution as 2 into 10 raised to 5, and maintaining some consistency with respect to the 10 raised to powers along with the nodal numbers. Okay, nodal degrees of freedom I have to once again mark it in the rows, corresponding rows and corresponding columns. So how will you get that? By looking at the FEA model. So in the FEA model for the element 1, the connectivity exists between node 1 to node 2, that is displacement 1 and displacement 2. That's what I have written. What is displacement 1? That is U1, here it is U2, and here it is U3. So U1, instead of representing U1, I just written the number 1, number 2, 1 and 2. Okay. So corresponding row and corresponding column I situated with the corresponding degrees of freedom. Okay. So later K2. So K2 is equal to A2 E2 divided by L2, 1 minus 1 minus 1. So I am going to substitute the value of A2. So A2 is 100 mm square. Note down that correction. Multiply by 2 into 10 raised to 5 divided by length of the element 2, that is 100 mm. So if you do that and if you do the substitution, so once again I am going to get the same number. So that is 2 into 10 raised to 5. 1 minus 1 minus 1 1. So 2 3. 2 3. So how will you return this nodal degrees of freedom? By looking at the element 2. So element 2 is having nodal degrees of freedom U2 and U3. So that's why I should start from 2 and 3. That is 2 for the first column, 3 for the next column, and then 2 for the first column and 3 for the next column. So here you need to take care of all this. Yes. So that is if you are confusing, you just observe these conditions that we have. Used previously. Here it is U2 and here it is U3. Okay, this is what I am denoting here. 1 represents U1, first, second, 2, first, second. Okay. So similarly, if you go for the in-depth FEA model, you have to denote the loads also. F1, here it is F2, and here it is F3. Okay, and if you look into this axis, so axis system you have to represent in this way. Got it? So this is about the usual FEA model you have to consider. For your clarification, I have written all these things. Okay. Next, let us go through the what is that? Load vectors. So load vectors and displacement vector. As we seen in the previous case, so we are having 3 loads as I denoted F1, F2, F3, which is at each nodal points. So F1 is nothing but the force situated at the node 1. F2 is the force situated at the node 2. F3 is the force situated at the node 3. So if you look into the actual what is this problem? So F1. So here we are having don't have any external force. So that's why I chosen that as 0, and at load 2 F2 should be 1000 Newton, but it is in the opposite direction of the coordinate system. That's why I have to take it as minus 1000, and F3 should be positive 500 Newton, okay, because it is along the direction of X. And so I got the load vectors as 3 values, okay. Similarly, displacement vector, here we are having 3 displacement values, that is U1, U2, U3. So that's why I need to represent a column matrix with the same considerations, but we don't have any values because we should calculate all these things. Next, this is about the step 2. If you go for the step 3, that is developing equilibrium equations. So if you remember with the steps involved FEM, where I should calculate global stiffness matrix, global displacement vector, global force vector. Global represents we are adding all the elemental matrices, okay. So let's do that one. So if you do that one, it will be of this type. So here also, first thing is you have to initiate with the stiffness matrix. For the stiffness matrix, you need to go through the particular nodal degrees of freedom, that is 1, 2, 3, 1, 2, 3. Why it is 3 cross 3? Because we are having 3 degrees of freedom, U1, U2, U3. So I need to give the numbers for these locations. In order to do that, you have to look into the what we call this individual elemental stiffness matrix, that is coefficients of that particular position, A11, like this. So 1, 1, 1, 1, we are having only the number 1. So that's what I should write down here. And if you go back to the previous location, 2, 1, which is nothing but minus 1, and 3 to 1, we don't have any connectivity. If you observe here, from the first stiffness matrix, we don't have any connectivity 3 to 1. In the second matrix also, we don't have the connectivity 3 to 1. That's why it should be 0. And one more concept of what is called a stiffness matrix is it is a symmetric matrix. That is, diagonally, all the contents above the diagonal should be same as the below the diagonal. That is what symmetric matrix. So if you find out these positions, then you can easily substitute that in the lower diagonal values. But diagonal values will differ. Okay, so please take care of that. So I got it is 0. Since it is symmetric, I will apply that rule, minus 1, 0, and later on 2 to 3. Still, 2, 2. Let us look into this location 2, 2. So 2, 2. If you observe here, we are having one value, that is 1, 2, 2. In the second stiffness matrix, we are having one more value. So that's why it becomes 1 plus 1. Let us look into the 3, 2. 3, 2. From the first matrix, we don't have any connectivity. And the second matrix, we are having 3, 2, that is minus 1. And let us look into the other things also. 2, 3, minus 1, 3, 3, 1. And we don't have such connectivity from the element stiffness matrix 1. So that's why 3, 2 is minus 1 and 2, 3 is minus 1. 3, 3 is 1. Okay. So you should practice these things where we have to add the subsequent position by considering all coefficients of the element stiffness matrices, where we have to consider all element stiffness matrix. Okay. So if you remember that the global stiffness matrix, this is stiffness matrix globally, and multiply by stiffness, what is that? Nodal degrees of freedom, that is displacement vector, U1, U2, U3, and thereafter that should be equal to F. So F positions that we already taken, that is 0, minus 1500. So this should be 0. This should be 0. Okay. So all the contents that I have maintained in terms of KQ is equal to F. Okay. So once the global equilibrium equations we have developed. What is the step 4? Next step, applying the boundary conditions. So step 4 is applying boundary conditions. So in order to do that, so we have to look into the actual diagram. So if you look into the actual diagram, no, leftmost end is fixed, that is node 1 is completely fixed. Since node 1 is completely fixed, so u1 should be equal to 0. Okay. So once you got that u1 equal to 0, next thing is you have to apply the elimination method. Okay. So elimination method that you have previously seen, the degrees of freedom related to the u1 should be eliminated. Okay. That is column and rows. The one column I am going to eliminate, terminating, as well as one row I am going to eliminate completely. Okay. So this one and this one. So if you eliminate that, which is the things that is left, 2 into 10 raised to 5, here it becomes 2, minus 1, minus 1, 1. And u2, u3, multiplied by u2, u3, that equal to minus 1000 and 500. Okay. It is a 2 cross 2 matrix. So how will you solve this? By using the what is called the matrix method, where the previously what you did in the same way, you have to do the matrix multiplication, that is 2 into u2 minus u3, that is equal to minus 1000, and 2 into 10 raised to 5 multiplied by minus 1 into u2 and 1 into u3, that equal to 500. If you do that and if you solve that, I got u2 is equal to minus 2.5 into 10 raised to 3 minus 3 mm, and u3 equal to 0. So what is the next thing? So u3 equal to 0. Why u3 equal to 0? Because some portion of the load that you have to analyze always. Okay. Since you find that towards x direction, it is against y direction, x direction, there is maybe a possibility of u3 equal to 0. Okay. Yes. Next, what is the next step? That is computation of elemental stresses and strains. So in order to calculate this, we should have the equation of stress, that is sigma 1 equal to E1 divided by L1 multiplied by minus 1 1 U1 U2. So I know all the values, just substitute that. 20 10 raised to 5 divided by 200 minus 1 1. So I got the values of U1 as well as U2. So U1 is 0, that is because it is fixed, and U2 from the calculation minus 2.5 into 10 raised to minus 3. So if you do the substitution, I am going to get it as minus 2.5 megapascal Newton per megapascal or Newton per mm square. Next, sigma 2 is equal to E2 divided by L2 multiplied by U2 U3. So you need to remember these things, why I am taken U1 U2 and U2 U3, because element 1 is connected to first node and second node, that is U1 U2. Second element connected to U2 and U3. So that's why I have chosen these values. Okay. So E2 value, I know that it is 2 into 10 raised to 5 divided by 100 minus 1 1. So what is the position values of U2? Minus 2.5 into 10 raised to minus 3 and U3 is 0. So I got 5 megapascal. So I observe the values also. Sigma 1 is minus 2.5 megapascal, which is compressive. Sigma 2 is tensile. Okay. So this completes the problem related to what we call stepped bar condition. Okay. I hope this problem you are getting. So hope everyone will solve this problem. So try to do that. If you get any issues related to solving, you just contact me. Thank you everyone for your patience listening.